Good morning. Welcome back to High School Algebra 1. For those of you that are tuning in for the first time, my name is David Dye. I am currently in my third year of teaching, second year at Algebra I High School, and this semester I am currently teaching algebraic connections and discrete math. So the last 2 weeks we've focused our attention on Critical Standard 1. This week and next week we're going to focus our attention to Critical Standard 2, where a lot of our focus is going to be about the graph of quadratic functions, identifying key characteristics, and then thinking about their transformations and how we can represent those transformations algebraically. So with that being said, last week I left you with some questions to think about getting ready for this week. And those questions were, what is the general shape of a quadratic function? In what ways can we transform the graph of a quadratic function? And what information is illuminated or highlighted whenever we're looking at the equation of a quadratic function? So I'm hoping today we can look at some of these things and answer those questions. So my learning goal for you is that we're going to be able to look for patterns in how the graph changes. The graph of these quadratic functions are transformed, and then make those connections to how they are represented, those transformations, in the equation of a quadratic function. So, the agenda. We're going to revisit some prior knowledge. I'm going to try and activate some things to get us ready for the lesson. We're going to look for patterns and structure within the graphs that I'm going to show you, and then I want to make connection to the structures of the algebraic equations to the shape and or shift that is occurring within our parabolas, our quadratic functions. We'll summarize the lesson and then look ahead to next week. So, as we think about revisiting prior knowledge, I want you to take a look at this image, and I want you to think about what you notice is happening to the frog across these images. So starting with image 1 over here, ending in image 5, what do you notice is happening? And so as we think about what's happening, I want you to recall some lessons from middle school and think about transformations. If we're looking at the frog in image 1 to image 2, we can see that this frog has been moved to the right and moved upward. So I'm shifting right and then shifting up. From image 2 to image 3 and then down to 4, it looks like we're turning our frog. And then turning it again all the way down to 5, but then it looks like we're flipping it. So I want you to pay attention to some of those words that I'm using, this idea of sliding it or shifting it right, up, turning it, and flipping it. And I want you to think of what type of language we can use to describe the types of movement that are taking place. And so there are general terms for these types of transformations. When we're looking to describe how something is moved right and up, left and down, those are called translations. When we're turning objects, like we are in 2 to 3, 3 to 4, and 4 to 5, those are rotations. And then when I try and get an image from 1 to 5 where it's kind of reversed, we call that a reflection. We flipped it, so we're reflecting it. And those terms are going to come up as we continue to look at some of these graphs of quadratic functions. So looking for patterns and structure, what I want you to pay attention to is what patterns do you notice in the following table of values. So this table here is a table of values for the function f of x is equal to x squared, where the left-hand side, my x column, are the inputs, and on the right-hand side are the outputs, the f of x values. So what patterns do we notice in this table of values? For those of you who are watching on YouTube or have the opportunity to pause, I want you to do so and take a look at that. But I'm hoping for those of you that are looking at the table that you notice this 0 here is going to be the lowest value in terms of our output column. In addition to that, you might see that there is some repetition on each side of the 0. You see the 1s repeating and the 4s repeating. And then another pattern that you might have noticed is that these values seem to decrease, 4, 1, 0, and then increase 0, 1, 4. So let me show you what the graph of this function looks like. And these dots here are the points from the table. How are the patterns that we just described related to this particular graph? What kind of connections can we make? Well, if I'm starting with this 0 as that lowest point, that lowest value here, it's also the lowest point on our graph. So there's that connection in that first kind of observation. Second, we notice that these values start repeating themselves. 1 and 1, 4 and 4 on either side of that 0. and we can kind of see that there is this symmetry along our parabola. They look to be reflected and images of each other. And then lastly, if I'm looking at that last pattern we described, how the values are decreasing, going from 4 to 1 to 0, and then from 0 to 1 to 4, we can see on the graph that it looks like it's decreasing down here. At 0, it comes right back up again, increasing. So what we see in the table of values is exactly what is illustrated in our graph. And I want you to continue to pay attention to those structures here in this equation, table, and then how it's represented within our graph. What I'm going to show you next are a series of pairs of equations, pairs of graphs, and pairs of tables. So I want you to look for differences as I'm showing these to you, and let's see how we can make connections to what we saw originally. In this part A, that dotted graph is the original x squared function that we saw on the previous slide with the same exact table of values. But now we want to compare that to this function x squared minus 3, and that's the graph in black. So if I'm looking for the differences between the two equations, the obvious difference is that this one here has this minus 3 as a contrast to our original function just being x squared. So how does that affect our two tables? If I'm looking at the inputs, for both tables they're the exact same, -2, -1, 0, 1, and 2. But our outputs have changed. We go from 4 to 1, from 1 to -2, from 0 to -3. And if you notice, all of the values here are 3 less than the values that we started with, which is exactly what we see in our equation, the -3 in that equation. And when I'm looking at the graph, we started here with our original x squared, and our graph has now moved down 3 units. So this one transformation has affected every aspect of our graph, and we can also see that these patterns that we notice also continue to hold. This -3 is the lowest point on our graph initially. We also see these values repeating themselves, the -2 and the 1. And so the symmetry is still holding within our parabola. Let's take a look at another pair. And I want you to compare this set of representations in B to A. What similarities are there? And specifically, I want you to pay attention to the fact that this -3 and this -3 are both in each equation. However, the location of that -3 has affected how our graph has moved. When the -3 was on this outside of our x squared function, our graph shifted down. But when the -3 is within these parentheses, our graph now has moved to the right. So this x minus 3 has caused a shift in our original x squared function to move right 3 units. If I'm looking at the table and trying to discern the differences here, our outputs are the exact same values, except our inputs now have shifted to the right 3 units so that our graph stays the same. I want to look at C now and compare that to B. What similarities exist here compared to B? And if you notice, this +2 also occurs within parentheses like we see in B. But notice that this addition of 2 has caused our graph, the dark bolded one, to shift to the left 2 units compared to our original x squared function. So if I'm looking at C and I'm looking at B, when I'm applying this transformation within the parentheses, my graph is behaving inversely to the operation that we see. I'm subtracting 3 and my graph moves to the right 3 units. I'm adding 2, but my graph moves to the left 2 units. Okay, let's see if that continues to hold true on the next slide. So here, let's take a look at D and E. So how do these pairs of representations differ or compare to the previous 3? Well, when we're looking at A, B, and C, we only had one transformation occur. Either I was subtracting 3 or I was adding 2. But when I'm looking at D and I'm looking at E, we've got multiple things occurring at the same time.
I didn't get that.
What we're seeing in D is that I've got this +2, so my graph starting from the dotted to the bold, moved up 2, and then this -1, moving it to the right 1 unit. And then in E, I'm moving down 4 units, and then to the left 3 units. So I'm combining a couple of different transformations in both of these graphs. And another thing I want to highlight is that the vertex, so this point at the very bottom of each of these parabolas, is still going to be apparent in our tables. So this 1, 2, this -3, -4, and it also is represented within our equations, something that we're going to look back at in a couple of slides. So, how do these representations compare to each other? Well, let's pay attention to the signs in these structures. Here I'm adding 2, so I shift up 2 units. Here I'm subtracting 4, and I move down 2 units. So those additions and subtraction signs on the outside of our function behave like we would expect them to. But like I mentioned before, the -1 within parentheses and the +3 inside the parentheses cause a shift in the opposite direction. This -1 has moved our graph to the right 1 unit, and the +3 in our parentheses has moved our graph to the left 3 units. Okay, so we want to pay attention to the signs and their location to determine where our graph is moving. As we continue to look for patterns and structure, so taking a look at this representation here, how does f compare to the previous ones? And if you notice, in this function, I've got this negative x squared. So I've got a negative value in front of x squared. I've got a coefficient that is negative, and look at what happens to our graph. It looks like from where I started in x squared, it is flipped. Pay attention to what happens to our values. Everything started positive, 4, 1, 0, 1, and 4. But then when I made the equation negative, all of my outputs also became negative. Okay, so that negative value flipped our graph and then changed all of the corresponding output values. But when I look at G and H, you also see, when we're trying to compare these, that these have negative values also that lead to that flip. And then the shift, the +3 and the -3 on the outside, have moved our graph up or down. But now I want you thinking about how we can use these other representations to complete the table. So I've got some missing values in here, but how can I use what we have, either the graph or the equation, to complete these tables? And let's think about some of the patterns that we've noticed in terms of the numbers repeating themselves and the graph being symmetrical on either side. If I'm looking at G, so we see this -2, -1 point. If I'm going over to -1, then I also see that this value here is going to be a 2. But I don't have to do any more work to try and find this one, because if it is a quadratic, which it is from what we see, this value is going to be repeated. So the 2 goes here as well as in this blank space. And we can use the same approach in H. Now, we can't really see the rest of this graph, but what we can do is plug the value of -2 in for x and then solve that. So if I square -2 and end up with a +4, this negative coefficient on the outside makes that a -4. -4 minus 3 gives us 7. And again, with the symmetry of parabolas, the 7 is going to fill in that spot as well as that bottom missing cell in our table. So we want to make use of the structure of our equations and our graph in order to complete these tables. Let's take a look at a couple more. So here we're looking at J and we're looking at K, and I want you to compare these representations to what we've seen previously. Before, with the other representations, we didn't see a coefficient that was in front of x squared. We didn't see any kind of number that was in front of x squared. So how do these numbers affect the shape of our parabolas? If I'm looking at 2x squared, let's look at the outputs in our table. My inputs still stay the exact same. I've got -2, -1, 0, 1, and 2. So those are pretty constant. But when I'm looking at the outputs, going from 4 to 8, 1 to 2, those values have been doubled, multiplied by 2. And look at the shape of the graph. The x squared, the dotted function, seems to be wider than the 2x squared function. The 2x squared function seems to be a lot more narrow than the x squared function. And that's because these values are a lot larger. So we see it kind of stretching in that direction. When I'm looking at 1/2 x squared, and I'm comparing these outputs to the original outputs, 2 is half of 4, 1/2 is half of 1, and we see on the graph that this particular function is a lot wider than our original x squared function. And so when we have these leading coefficients, the shape of our graphs are changing. Whereas before, when I'm just looking at these transformations, the only thing that's changing is the direction. Is it facing right side up, or is it flipped? Have I moved it up? Have I moved it down? But nothing until we apply these leading coefficients to x squared does it change our shape. So we want to pay attention to those structures, right? And when I've got this value that's bigger than 1, 2, we see that the shape of our graph is a lot more narrow. But when I've got a fraction, a value that is less than 1, we see that our graph is getting compressed. It's a lot wider. And so if I'm trying to make the connection between these transformations and the vertex form of our quadratic function, something that we talked about last week, we want to think about what information about a parabola is highlighted within that particular equation. So here we've got this y is equal to 1/4 times the quantity x minus 3 squared minus 4, and here's our graph. So what information can we tell? Based on this equation and based on this graph, the first thing we can tell is that our graph has been translated horizontally, so I'm moving right 3 units. In addition to what we see in our equation and on our graph, we can tell that it has been transformed and moved vertically down 4 units. But what else can we tell? We've looked at the 3 and we've looked at that -4. What about this 1/4? Well, it's a positive value, so we know it's going to open up. Now, if it was negative, it would flip and open downward, but because this 1/4 is positive, it opens up. And because that 1/4 is less than 1, we can say that this graph has been compressed compared to our original x squared. And lastly, that 3 and -4 that we see in our equation are the exact coordinates of the lowest point on our parabola. And that's going to hold true every single time in this form. But you want to pay attention to the signs. So this -4 still holds true as far as our coordinates go, but this 3, remember, the sign changes, so that's got to be a +3 when we're recording the coordinates of that vertex, that point, in this case the lowest point, the minimum point on our graph. All right, so let's make sense of some of these structures, and we want to compare how these things are to the original parent function of x squared. So when I'm looking at this function, x squared plus k, and I'm going to say k here is any number that's not equal to 0, because if it is 0, then we're just left with x squared, our original parent function. So when we're talking about k not equal to 0, we're talking about a translation that is vertical. I'm moving my graph either up or down, and we saw that in our first couple of slides. And it behaves like we think it would. If the k value is positive, we're going to shift up. And if the k value is negative, we're going to shift down. So it behaves like we think it would whenever k is on the outside of x squared. Let's take a look at another piece of structure. So again, we're comparing it to our parent function x squared. But what happens when that transformation occurs within the parentheses of our function? So here we're looking at something x minus 8h, that quantity squared. And h again is any number that's not equal to 0. So when we're talking about this, we're talking about a translation that is horizontal. I'm either moving left or moving to the right. But again, we've got to pay attention to our signs, right? So when h is negative, so minus h, my graph is going to shift to the right. But on the other hand, if h is a positive value, if I had x plus h, x plus 3, my graph is shifting to the left. So when we're talking about these translations that are horizontal, moving left or right, the sign is going to indicate a shift in the opposite direction. So you want to pay attention to what we're seeing sign-wise within the parentheses. Again, we want to compare what happens when I've got a leading coefficient in front of x squared. And again, we want to talk about when that value is not equal to 0. So when a is any number that's not equal to 0, we're going to talk about this dilation. We're changing the size of our parabola. So we're either stretching it and making it more narrow, or we're compressing it and making it more wide. Before we get into some of those things, we also talked about when a is negative, this graph is reflected. We flipped our graph before, and so you want to think about whether or not this leading value is a positive or negative value also. And as we looked at earlier, whenever we have these fractional values, we notice that our graph gets compressed, and we're going to call that a vertical compression. And when a is a value that's greater than 1, like that 2, we saw that our graph became more narrow, and we're going to call that a vertical stretch. So the vocabulary here is something that we need to pay close attention to when we're talking about looking at the structure of these things and trying to make sense of it. All right, so let's summarize some of the things that we talked about. Now, the vertex form of a parabola as an equation is represented as this function. F of x is equal to a times the quantity x minus h squared plus k. And that's something I introduced last week. So when we're looking at the values of h and k, that's going to describe how that function has been translated horizontally, left or right, and then vertically, up or down. Okay, so I'm looking specifically at these values of h and k. And then with that, because I know the translation, whether it's horizontal or vertical, I know the coordinates of my vertex. That value, or that coordinate point, is going to be the values of h and k, respectively. When I'm looking at the value of a, we know that it describes whether or not that vertex is going to be a minimum, whether the graph is opening up because this is a positive or negative value. And if it's opening down, then obviously it's a negative value, and we've got a maximum point. All right, so those are some of the structural things from this equation that we can tell about our graph. Now, as we look ahead to next week, again, I want to focus your attention on some questions. So what are the key characteristics of a parabola? We've talked about that vertex today. We've talked about intercepts last week. And I talked about this idea of symmetry, but what other key characteristics of a parabola are there for us to explore? And then today we focused our attention mostly on the vertex form of a quadratic function. So when we're looking at other equation types, the factored form and the standard form, what other characteristics about a parabola are given to us? That's all the time we have for today. I will see you all next week.